Alright, in this final section of chapter 4, they put it all together by finding all the zeros for both real and complex for a polynomial function. And so we said earlier in the last section that the degree of the polynomial, that's the maximum number of real zeros. Well, if we go to the complex plane, it actually achieves all those. And so we get, if it was a 7th degree polynomial, we would get 7 complex factors, right? Some of them will complex, I guess, includes the real numbers. Not I guess, it definitely does. But what we mean by complex is when it's of the form a plus bi, where a and b are real numbers. So 5 is in the complex plane, and so is 7i, and so is 2 minus I. It's these ones right here, these imaginary ones, that we're going to be after. But something that you need to realize is that as you have a true complex number that has an imaginary part, the zeros come in complex pairs. They come with their conjugate. Now that should be a familiar term for you. You would have used the conjugate in both the Algebra 1 and a beginning algebra and an intermediate algebra class to simplify this, to get rid of the I out of the denominator. Actually, it would have been just an intermediate algebra class. And you'd multiply by the conjugate 2 plus I. So that's what I mean. If you have a root, they come in these conjugate pairs. So if they tell you that a root is 7 plus 3i, then you know another one has to be 7 minus 3i. There's no way it couldn't come with its conjugate pair if it came from a nice polynomial function. So what they're going to do is just reinforce this along the way. This is actually a little bit easier than the last section, I think. So for example, this is the first example that I saw. So I'll call this example 1. So for example 1, what they tell us is that we have a degree 3 polynomial. And this is very similar to another section. And they want you to find all the zeros. Okay, and so they give you some zeros. They give you, given 8 and negative 4 minus I are 2 of the zeros. And they want you to find the third. Well, you're done. Because you know that if you have a third degree polynomial that has these two roots and it has just one more, and that one more has to be the conjugate pair of negative 4 plus I, right? Where you would just switch the sign on the I. I just wanted to go up to make sure I didn't drop a negative up top. Yeah, there was no negative on the first thing. So that's it, negative 4 plus I. You're done with that problem. They just want to reinforce that. Example 2. Here we have a degree 6 polynomial. The given zeros are 3, 5 plus 9i, negative 8 minus 3i, and 0. So we're given 4 of the 6 roots, but you know what the other ones are. So the other ones that we have to find are easy. 5 minus 9i and negative 8 plus 3i. And you're done. Awesome. Example 3. Now it does get a little bit more complex as we go along, and we'll see that build up, but nothing too outrageous. They're telling us that we have a degree 4 polynomial, and we have the given zeros are 3, but it has multiplicity of 2 and 2i. Well, then we know the other root is negative 2i, right? That's what we had to find. But they're also going to ask us find a polynomial that has these roots. And this is where the time's going to come in for this section. But it's nothing more than being back in, honestly, a pre-algebra class doing FOIL. So here's what you know. You have a polynomial who has a root of 3 that has multiplicity 2. You know one of its roots is 2i and the other is negative 2i. And so you're going to multiply that out. Now, it's a little bit, I mentioned that it was pre-algebra. Pre-algebra in terms of the work that you have to do. Because of the i's, it's technically intermediate algebra. But let's go here. You know this. These are conjugate pairs, so we get x squared minus 4i squared. Right? It would just be the first thing squared. You'd have no middle term. I mean, you can FOIL it all out, but your experience by now should know that there's no middle term. And then you get the last thing squared. And then this is still x minus 3 squared. All right, I'm going to keep this. Actually, I'm going to square out this x minus 3. We know that as x squared minus 6x plus 9 times, and let's clean this up, x squared plus 4, right? Because I squared is negative 1. And now what we have to do is just run our x squared through, x to the 4th plus 4x squared. Run our minus 6x through, negative 6x cubed minus 24x. Run our 9 through, 9x squared plus 36. Awesome. Not done yet. We got to combine like terms. I'll put it in descending powers of x. That's what they refer to as standard form. 4x squared and 9x squared, that's 13x squareds. Negative 6 and negative 24x, right? There's no other x in there. And then a 36 coming through. So we just combine those like terms. So you'll type that in, that last polynomial there, in order to get credit for a polynomial that would have those roots. Obviously, if we doubled everything, it would still have the exact same roots because we'd factor that out. So this is just one of an infinite number of ones that can be adjusted. All right. So that's going to be one type of problem in there. Here's the next step, example 4. In example 4, they give you a polynomial, h of x is equal to 3x to the 4th plus 13x cubed plus 2x squared plus 52x minus 40. And what they tell you is that they give you 1, 0. So I'll put given. The given 0 is negative 2i. Well, then that's it. And so what they want you to do is find the remaining zeros. Well, we know 1. Right away, we know 2i is 1. Okay, so we'll type in 2i, but there's 2 others. So what are we going to do next? Well, we're going to look at this factorization. We know h of x is equal to x minus, well, I'll go root by root, x plus 2i, the one that they gave us, times x minus 2i, times some other polynomial. And it's this polynomial. Now this would be a quadratic, right? Because we'll pull out 2 x's times some quadratic polynomial. So that we can solve any quadratic. So what we need to realize is that this is x squared minus, I'll take it step by step so I don't lose anybody, times this quadratic. We're after what this quadratic is because that's going to give us the other 2 roots, but we're going to need to step through this window. So this is x squared plus 4 times the quadratic. So what we know is that this x squared plus 4 goes evenly into it. So guess what we have to do? We have to do the long division. So you could have been upset at your beginning algebra teacher, intermediate, in all of this process, but we don't want you to be. They made you do this long division. Well, they did it for a reason. It's absolutely a tool that we need. So let me put this x squared plus 4 a little bit lower. And we'll come here and I'll write in the 3x to the 4th plus 13x cubed plus 2x squared plus 52x minus 40. And it should go in evenly into this. So let's try it. Just double checking that it didn't mess up any signs. So 3x squared would be our first guy. We would get 3x to the 4th plus 12x squared. And we would do the subtraction. So we come in here, and I'll do it in red, subtract, subtract. And what do we get out of this? We get a 13x to the 3rd positive. Guess I didn't need to write the plus in there. we get a 13x to the third, and we get a minus 10x squared plus 52x. I'll bring that one down as well. So what are we going to add? We're going to add 13x cubed. And we'll get 13x cubed. And we get 4 times 13. And 4 times 3 is 12. So we're going to get a 52x out of that guy. We're going to subtract. Again, I'll do that in red. So we know that you are attention to detail based upon the major that you chose. So this is all good work for you. Right? Both of those cancel out, and we're left with that. 10x squared minus 40. Well, we know what makes x squared go into negative 10x squared, a minus 10. And when we run that through, we match it exactly. So when we do the subtraction, we end up with a 0. And so now we know what this quad is. So I'm going to come right back up here. I'm going to erase the word quad, and I'm going to put in what we know. We know that it's times 3x squared plus 13x cubed minus 10. Oh, I put 13x cubed in there. Sorry, you're probably super mad at me. It's not an x cubed there. It was an x, right? I was thinking about the result of that. It was 13x. Awesome. So way better. So we're done with this. So now where are we? We're back to beginning algebra at the very end. And I'm naming the classes just so you know how much we're relying upon. Nobody's teaching you how to factor again. We know that you have that skill, having reinforced it at least over 2 classes, but probably many others. So we already knew the roots that are coming out of this guy. Let me show you what this guy is. Sorry. This guy right here has the roots 2i and negative 2i. What we need is the additional 2 roots out of this last thing. So we're wondering where, and let me come in here in red, we're wondering what other 2 roots come out of here. We're wondering when does 3x squared plus 13x minus 10 is equal to 0? Because wherever it is, that's going to be our factorization. Or how does it factor? That might be another way to look at that. Does it factor? Are there factors of 30 that subtract to be 13? Oh yeah, 15 and 2. So perfect, we know how it factors. This is a 3x and an x. I need to get a 15 out and a 2 out. My 15 needs to be positive, my 2 needs to be negative. And we're finished, right? Using algebra 1, using beginning algebra. This would be a beginning algebra problem because it completely factors. So the other 2 roots are 2/3 and negative 5. And so you'd put all that together, but you have that work in there. And so it's really good, right? Because it's getting us to think. I do want to model one last one as we go through here. Let's take a look at something like, well, like this. This is my 5th example. F of x is equal to x cubed minus 11x squared plus 43x minus 65. So we know this thing's going to have 3 roots. And it's saying find all the complex zeros. That's it. Doesn't give you any. Find all zeros, both real and complex. All right, they didn't give us any. So Descartes' rule of signs says that, well, what's it say? Are we going to have any positive ones? 1, 2, 3. Oh, we're guaranteed to have a positive one. It's because it's 3 or 1. That's where I would start. Now, what's super nice about this problem is that there's a 1 in the first position. So the things that we have to try are either plus or minus 1, plus or minus 5, or plus or minus 13, the factors of 65. Oh, apologize. One other set, plus or minus 65. That's it. So I would totally do synthetic division and grab the positive something in here. So this is 1, negative 11, 43, and 65, but the 65 is negative. Okay, and so we could start with something like 1 and see if 1 works, but we know there's a positive one. So I would start low. So if I bring down the 1, 1 times 1 is 1, Negative 11 and 1 is a negative 10. Then I would get a negative 10 and a positive 23, but that's not going to hook up to be the 65. So it's not the 1. So again, we're doing this in pencil, and we're taking out the 1, so now we know it's definitely not positive 1. Let's try positive 5, right? And so it's going to be nice, because if I find one of the roots, then I get a quadratic, and I can do anything with the quadratic. Use the quadratic formula if I feel stuck, something like that. And again, all we need to do is find the zeros. So bring down the 1, 5. 5 minus 11 is negative 6. Then I get a negative 30, which brings me to a positive 13. Oh my goodness. 5 times 13 is 65, and I get a remainder of 0. Awesome. We now know 5 is a 0. So we definitely know 5 is a 0. And we know the other zeros come from this polynomial. Now what is that polynomial? Again, you drop the power 1, so it's x squared minus 6x plus 13. We need to figure out where this is 0. Now the question is, does it ever equal 0? It doesn't factor. There are no factors of 13 that add to be 6, so they're not going to be pretty. They're going to either be, what's the right word? I want to say improper, but that's not it. Irrational. Okay, they'll either be irrational, involve a square root, or they're going to be imaginary. So let's see. Personally, what I would do is not the quadratic formula. I think I could do it faster if I moved over the 13 and then completed the square by adding 9. And you can see already that it's going to be complex, but we're going to get it. This is x minus 3 squared is equal to negative 4. That negative 4 is what makes it complex. We're going to take the square root of both sides and get plus or minus 2i. So what's left to do? Only to move over the 3. I think that's far faster than going through the quadratic formula. When you have a 1 in the first position and an even number in the middle, completing the square, if you're comfortable with it, will hands down beat it. And guess what you have? The other two factors. I don't know if it allows you to do the plus or minus. When I listed them out to just see what the format was, I listed them out separately like I have them here. But you're finished. You got all of those zeros. So that's awesome. This is the type of work that you're doing in 4.7. Should be good. It's going to tie in the 4.6 ideas as well as the whole idea of conjugates. The biggest thing to remember that we've used consistently throughout all the examples is what I wrote up here. Zeros come in complex pairs. So if there is an imaginary one, it'll have its conjugate as its complex pair. All right, have fun in 4.7 and look forward to that exam that's coming next week.